All right. Well, howdy, folks. Welcome to the first of many COMP40 remote lectures. Thanks for tuning in. Just some notifications at the start here. I do have a little cursor that I'm going to be using to indicate things on the slides as we go. Unfortunately, because I'm using Google Slides, if I go into the bottom area, this little box pops up, but I don't think that should really cover up any important information. And if it does, the slides are also posted so that you can follow along with this if you like. And then there will be a class session where I'll be hosting a Zoom meeting during our normal class time where you can ask any questions that you might have about this lecture. I strongly recommend that you have some paper or have another document pulled up so that you can take some notes about or write down any questions that you might have as we're going along. Finally, one annoying caveat, there is construction being done outside of my apartment, and no information is given about when it will start, when it will stop. So if you hear some odd additional noises, it is most likely that construction. I apologize for that, but hopefully it won't be too distracting. All right, so let's get started. Today we're going to start diving into the universal machine, or the UM, which is going to be the focus for the rest of your assignments in this class. So let's get some context first of where we are in the course. So here's the familiar COMP40 roadmap. We already, through the first couple assignments, ramped up your programming skills and dealt with some big programs that taught you some of the core concepts in COMP40. And as of when you're watching this lecture, you've either completed or are scrambling to potentially complete the BOM, which gave you some really in-depth understanding, hopefully, of one of the most common assembly languages today, Intel's x86 assembly language. Now that we have some familiarity with assembly and the machine code that it represents, we can actually start designing our own machine architecture and emulating it in software. But what is an emulator? Well, here's the definition that we're going to be working with. An emulator is hardware or software that implements another machine architecture, some other machine's architecture. Here, with the universal machine, we're going to be dealing with a hardware emulator that's written in software. Now, thinking about emulators can get sort of mind-melty. So I have an example that will hopefully make it clear what they really are and how to think about them. So to understand this, to understand what an emulator is, we first have to consider some machine architecture that's different from ours, right? Our hardware, our x86 architecture, and a software program that we write will somehow together implement a different machine architecture. So what's another machine architecture that exists? Well, most video game consoles, like this Nintendo 64 N64, have dedicated instruction sets that are used to guide the hardware inside of them and actually execute the code for certain games. So the N64 is a video game console that was released in 1996, and it contains a processor so that it can play games. Specifically, it contains hardware that can execute instructions from the N64's instruction set. The possible instructions it could execute were different from our now familiar x86 instructions. Just as our machines execute instructions found in programs, so too does the N64. However, its programs came in the form of physical cartridges. Each cartridge contained a chunk of read-only memory, or ROM, and this ROM stored the instructions that, when executed, would let a user actually play the specified game provided by the cartridge. To play the game, you would insert the cartridge into the console, which would hook up the chip in the cartridge to hardware in the console. When you then turned on the console by flipping this little switch over here, the hardware in the console would start performing the traditional fetch, decode, execute cycle that our CPUs still perform today. It would perform this cycle on the instructions that were stored in the cartridge's memory, letting you actually play the game through an I/O device provided with a controller that would be hooked up in these ports here. So the N64 provides an example of one kind of machine architecture. Specifically, its processor executed instructions from the MIPS instruction set architecture. My laptop, by comparison, has a processor that runs the x86 instruction set architecture. So given instructions for the N64, my laptop will have no idea what to do with them. Even if I had some sort of special device attached to my machine that could read an N64 cartridge, it wouldn't be able to actually run the code stored on the cartridge. Bummer. But what if I want to play an N64 game on my computer? Is it completely impossible since my processor in this machine and the N64 processor in that machine don't speak the same language? They don't speak the same instruction set. The answer is not at all. There's actually a couple different ways that we can still somehow play an N64 game on a machine that doesn't have N64 hardware. One way I could do it is to simulate an N64 game on my computer. Here's how this would work. I could write a C program represented with this goofy little box int main here. And that program could somehow capture the software present in an N64 cartridge. If I run this C program, I want to see a window pop up on my screen, maybe over here, that makes me think I'm playing this game just as if this was a TV screen hooked up to a real N64. In order to make that window pop up, I need to run my C program, and the program will be executing on my laptop's hardware. I don't need a physical N64 at all. Finally, as the program is running, I'll maybe attach a controller through a USB port on my laptop so I can actually play the game. My controller's output, the buttons that I press, will send signals into the machine, and it will provide input for this C program that I wrote so that it knows, say, when I'm telling my character to jump or move around. This is simulation. What we're going to be doing is emulation, which takes this concept one step further. If we wanted to emulate an N64 on my laptop, here's what we would do. Instead of writing a program that simulates the specific game I want to play, I would write a C program that simulates the N64 hardware itself, that somehow simulates the processor and the memory being used inside of this device. I would have to create abstractions for the CPU, the memory system, the graphics and audio cards, and then implement those abstractions in C code. I would then run this C program on my laptop just as before, and executing the program would amount to turning on the N64. There's no physical N64 though. I've written a program to exactly emulate its execution process. But without a game, this emulator won't do anything interesting. Just running this program by itself is like turning on the N64 with no cartridge in it. So the question is, how can I provide a game if I can't hook up a physical cartridge to this machine somehow? Well, the cartridge simply stored instructions for the N64 hardware to execute. So if I can put a sequence of N64 instructions in a file, say, that's what this rectangle represents, a file, and I code up my emulator, I write my program to read from this file, then I can pass the file as an argument to my C program and watch as my N64 emulator executes the instructions to play this game. This is exactly what you're going to be doing for homework 6, except instead of implementing an N64 emulator, you will implement an emulator for a different hardware architecture called the universal machine that we refer to as the UM. Your C program will emulate a universal machine, and it will take a sequence of instructions for the universal machine as input in a file. It will execute that UM program and produce whatever output a UM would produce if these instructions were actually executed on a physical universal machine. In designing and implementing this emulator, you're going to get a deep understanding of the different parts of a specific machine architecture and how they interact to form a working computer. Visually, here's what our emulators are going to do. This is a picture, the classic picture we've been seeing of our machine architecture. Our machines have their own processor, their own CPU, and their own memory. That's how they operate. You're going to write a program in software that captures all of the components of a its registers, its ALU, its memory system, and its fetch, decode, and execute cycle. That program will then execute on your machine's CPU just like any other C program that you would write. But here's why it's a little bit mind-melty. The program you write is itself a full machine that is being run by another machine. So it's a little inception-y. Take a moment now, pause this video if you like, and write down any questions that you might have about the notion of emulation or the general idea of what we're going to be doing to emulate a All right, let's keep on going. So you're going to be emulating a which stands for Universal Machine. The full details of the are included in the spec for the assignment, which I heartily recommend that you read at your earliest convenience. For the rest of this session, I'm going to explain the components and how they work from a high level. Again, as I'm going, please write down any questions that arise so you can ask them in our scheduled Zoom meeting during class time. Down here on the right is our little cartoon of the CPU, the cache, and main memory that we've used all semester. As I introduce new aspects of the that differ from our standard architecture, I'll update this picture accordingly. All right, so let's get started. The has a load store architecture, which is actually the same as our x86 machines. This just means that all computation has to be done in registers. So if you want to do computation on a piece of data, but it's not in a register yet, you have to load it into a register from memory. And if you want to use a register, but it already has a piece of data in it that's needed for later, that data needs to be stored in memory before reusing the register. The is pretty tiny in its storage, in its direct storage at least. It only has 8 registers, each containing 32 bits. So this does change our picture, paring down our register file here to only contain 8 registers. Since each one is 32 bits large, that means that the word size of the architecture is 32 bits. So the has 32-bit words. Those 32 bits can be interpreted in a few different ways. They can encode a single instruction. They can encode an address somewhere in the memory, and they can also encode just general unsigned integer data. There are no special floating point registers in the and there's no floating point instructions either. Next up is the memory system, which is quite a bit different from what we've covered in class so far, which is a traditional cache-based memory hierarchy with fixed size memory blocks. All the blocks in our memory system have the same size. Our memory system in the is called segmented memory, which changes our picture in a few ways. First, there's no longer a cache that's acting as an intermediary between the processor and main memory. Instead, the processor can talk to memory directly. This is another significant departure, is how main memory is actually organized. As I said, in most machines today, our memory system is block-oriented. Memory is broken up into fixed size blocks, and internal chunks of those blocks can be allocated and freed by a memory manager. In the memory is segmented instead of blocked. Here's what that means. All available memory can be thought of as a general pool that can still be allocated and freed. Here's our pool of memory, but it's up to the program to perform the allocation and freeing with instructions. There are 2 machine instructions that let you ask for memory from the pool and return it. The map instruction lets you ask for a new segment of memory to use. It's conceptually a lot like malloc, but it operates at the word size instead of at the byte size. So you specify how big a segment should be in 32-bit words, and the memory system will reserve a chunk of memory big enough to hold that many words. However, malloc is a software construct that you use in your programs. Mapping in the is a machine-level instruction that directly manipulates the hardware. We're going to see some examples of this in more details later in these slides. But visually, you can map multiple segments during the execution of a program, and each of them can be the same size or different, completely up to you as the programmer. Each of these gray boxes represents a segment that's been mapped, and each shows that can hold a different number of 32-bit words. Segments are where the memory that you can actually access lives, and we'll get into how to access memory in a segment later in this lecture. If you don't need a segment anymore, maybe you're done with whatever data you were storing there, you can unmap it with another instruction and return it to the pool of free memory. This is a lot like the free function in our C programs. You can provide an identifier. Each segment will have a unique identifier, naming it, and you can provide a segment's identifier to this unmap instruction, which will let you return that segment to the pool. So I just unmapped the segment using the identifier for the one that disappeared. This segment would have a different identifier. They're numbers, maybe it's like the number 10. So if I say unmap 10, that segment will be returned to the pool, and it can be used by later map instructions to generate new segments. Again, we're going to get into some more details on segmented memory in a bit, but be aware, this is the part of the that trips up the most students each semester. So make sure you try to understand the details about how segmented memory works in the spec and come to class with questions. Up next, the has the ability to perform byte-oriented I/O. You can sort of envision another hardware control unit in the processor that's hooked up to our register file. And this unit's purpose is to produce output from the CPU or take in input from the user and stored in a register. Output from this device will be hooked up to standard out in your emulator. So in your C program, whenever an output instruction is executed, you will be generating output on standard out, and input to this device will come from standard in. That's it for the I/O device. Again, it can only operate a byte at a time. Please read the spec for more details on how this part of the processor works and come with any questions you have. I'm going to just remove these parts of the diagram to make space, but they're still in our hearts. We will remember them fondly. Instructions. What can the actually do? Well, we already know two of the instructions are mapping and unmapping. We'll see examples of that later. And we also have two instructions for getting input and producing output. These 4 instructions are part of the total set. In total, there are 14 RISC-style instructions the can compute. RISC stands for Reduced Instruction Set Computer. Basically, we say that an instruction set is RISC style if we just have a few extremely simple instructions. Simplicity is things like adding, subtracting, multiplying, stuff like that. And this is in comparison to CISC style. You just replace the R with a C, which would stand for complex instruction set computer. A CISC style machine has way more instructions, some of which take a really long time to execute and are usually very specialized. An example might be an instruction just for doing the square root operation, or an instruction for doing, say, access this chunk of memory, add it to this other chunk of memory, and store the result somewhere else. Some just crazy nuts instruction. Just like big and little endian, the choice between CISC and RISC used to be a really hotly debated concept. But nowadays, it's been concluded that the choice of an ISA being RISC or CISC is largely irrelevant for the performance that you're going to get out of a processor. There's actually a paper written about this if you're interested in it. The title is ISA, the letters ISA Wars, sort of like Star Wars. Understanding the relevance of ISA being RISC or CISC to performance, power, and energy on modern architectures. Feel free to look that up if you're interested. So we're going to get into what all of the different instructions are on the next slide. But as we look at them, you might notice that some things are missing. Specifically, the omits some instructions that you might think are necessary to perform any general computation. There's no jumping or branch instructions. There's no subtraction, and there's no shifting to the left or the right. It turns out that we don't need any of these instructions added to the 14 that we already have. The just with these instructions and omitting these ones that we're used to, can still compute anything that our x86-based laptops can compute. This realization of the equivalence of the computing power of seemingly very different machines with different capabilities is actually a fundamental idea in the world of computer science. There's whole theses written about this, and it's one of the main conclusions that Alan Turing had when he was doing his work in the 30s and 40s. We're going to get much more into that realization in the next lecture on the It's pretty cool. All right, so this is at a high level all of the components of the For the rest of this lecture, we're going to first get into the actual instructions, and then we're going to talk a bit more about how the segmented memory system works. So now let's dive into the different instructions and how they're encoded in a universal machine word in the 32 bits that a can store in a register. So the 14 instructions can be divided into categories based on their purpose. I'm going to mention the categories and just list the instructions and give like a single sentence description of each. All of the details can be found in the spec. So please take a look at that, come with questions. So first we have some instructions for performing arithmetic and moving data around. We can add, multiply, and divide the contents of two registers and store the result in another register. We can load a value, so we can specify an unsigned integer number and a register, and the instruction will load that value into that register. So this is basically a way to sort of generate constant values in our registers to then do computation. We also have a conditional move operation, just like an x86, where we will move the contents of one register into another if some condition is proven true. The next set of instructions are all dealing with memory. As I alluded to earlier, we have two instructions that let us ask for new segments. We call that mapping a segment, which gives us back an identifier to uniquely identify that segment. And later on, we can then provide that identifier to an unmap instruction to say, we're all done with the segment with this identifier. You can put it back in the pool. We can also ask for memory, a word of memory from a segment that's been mapped, and we can load that into a register. That's the segmented load instruction. And we can also take the contents of a register and store that in a specific memory segment at a specific address in that segment. We'll see examples of these later. Finally, this is a weird instruction that can do something cool. You can specify an identifier for some other segment and say, take the contents of that segment and load it into a special segment that's used to store the instructions that that the should be executing. So we can basically overwrite the current program that we should be executing with new instructions in a new segment, and that will capture new instructions to execute. If that sounds confusing, again, we're going to see an example of that later. But this basically lets us change the program that we're running on the fly, which is sort of cool. We have one logical instruction. We can do a bitwise NAND operation. This is simply doing the bitwise AND of two registers, and then on the result, doing a bitwise not operation, so flipping all the bits in the result of the AND. That's the only logical operation, but it turns out that just by using NAND, you can actually encode all of the other logical operations, AND, OR, NOT, XOR, any of them. We have two I/O operations. We can ask for 1 byte of input from the user and get it through standard in, and we can produce 1 byte of output, and the is actually capable of producing ASCII characters as well. Finally, there's one operation that doesn't fit in any of these categories, and that's halt. You can instruct the machine to terminate, and that will end the program cleanly. Every valid program that doesn't terminate with an error should always end with a halt instruction. So all of these instructions, all 14, can be encoded in a word, which is how many bits long? Remind yourself how many bits makes up a word. The answer is a word takes up 32 bits. So here is a visualization of a word. And we can divide the bits into different components. So each instruction has a unique identifier called an opcode. And I'm representing that with OP here. And that lets us distinguish one instruction from another. If we have 14 instructions, how many bits would we need to give a unique identifier to each? How many bits do we need to count up to 14? The answer is 4 bits. With 4 bits, we can actually count 16 things. So we're being a bit wasteful, but if we only use 3 bits, we can only count up to 8 things. We need to count to 14. So we use 4 bits for our opcode. The opcode always takes up the highest order 4 bits of the instruction. The vast majority of these instructions also specify 3 registers that may or may not be used depending on the instruction. So we have 8 different registers in our 8 different registers that we could use. So how many bits do we need to uniquely identify a given register if we have 8 of them? The answer is 3 bits. With 3 bits, we can count 8 things. So the lower order 9 bits of this instruction are used to encode the 3 different registers that an instruction might use. So 3 bits are used to encode this register that we're going to call register A, another 3 bits for the second register, and another 3 bits for the last register, giving a total of 9 bits. The specification refers to the 3 registers that might be used in an instruction as RA, RB, and RC. And the bit value for, say, RA, the 3 bits found in this location, indicate which register is acting as RA for this instruction. So let's see an example to help explain that. The add instruction has an opcode of 3. So what that means is that the bits in the opcode field of our word will correspond to the value 3. There should be 1, 1, 0, 0, because that's the binary code for the number 3. The use of the 3 registers here is dictated by the specification for the add instruction. So here's what the specification says. Here's what the add instruction does. It says if we have the add instruction, if the opcode is the number 3, then the register named in the RA field, which is what this notation says, should get the result of our computation. And the computation says, take the register named in the RB field, add its contents to the register named in the RC field. So add all those bits together and store that result mod 2 to the 32nd in the result register. So if this instruction had binary values in these 3 locations that corresponded to the numbers 2, 0, and 7, so this one was 0, 1, 0, 0, 0, 0, and 1, 1, 1, encoding the numbers 2, 0, and 7, what this means is that RA should actually be register number 2, RB is register 0, and RC is register 7. So you use the contents of register 0, add those to the contents of register 7, mod the result by 2 to the 32nd, and store the resulting bits in register 2. Almost every instruction in the uses this format, where the highest 4 bits are the opcode and the lowest 9 bits name 3 different registers that may or may not be used based on the instruction. The rest of the bits in between are unused if this format is being used. There is one instruction. These are all the instructions that have that format, and there is one that has a different format. It is the load value instruction, which has an opcode of 13 shown here. That opcode still sits in the highest order 4 bits, but the rest of the instruction format is different. The next 3 highest bits still give the number of a register, and that register is where a value is going to be stored, where a value will be loaded. The remaining 25 bits are used to store the immediate value that should be loaded in this register. So when this instruction is executed, the unsigned integer that's represented by the lower 25 bits down here are loaded into the register that's named by this field in the instruction. So if this was, if the 3 bits here captured the number 5, that would say take whatever value is here, maybe it's the number 42, and store those bits in register 5. Take a moment now and review what I've talked about and write down any questions that you might have about the UM's instruction set or how those instructions are formatted into a 32-bit word. All right, so let's move into the next major part of the UM. It's segmented memory system. Again, a segmented memory system simply divides memory into variable size chunks as opposed to fixed size blocks. And as a result, it requires a different addressing scheme, which we're going to see. So you might be asking yourself, well, why are we having you use a segmented memory system in your UM? Why not just use the block-based approach that processors typically use nowadays? Well, there are some pros and cons to both using and implementing segmented memory. First, a segmented memory system can actually enable programs using small pointers to access a larger amount of memory than you would think. On our byte addressable memory systems, ask yourself, how many bytes can a 32-bit pointer access? How many unique byte addresses can a 32-bit pointer encode? The answer is 2 to the 32, right? If we have a 32-bit pointer, each bit could be on or off, giving us 2 to the 32 different choices. If instead our pointers say that we still have 32-bit addresses somehow, if they're simply addressing into a single segment, that means that that one segment could have 2 to the 32 different addresses in it. Well, if we can have multiple segments, then we can access potentially more than 2 to the 32 different things in our memory. We have to use 2 addresses at a time instead of 1, but that lets us address way more memory than just the normal single pointer-based approach could. Next, I don't know if you'll see this as an advantage, but it's actually pretty interesting to work out how to encode a segmented memory system. I had fun working on this assignment last semester, so hopefully you'll find it endearing as well. There are definitely some disadvantages to using segmented memory, though. It's a bit more complex to get right than a flat memory system, where you just have an array of contiguous blocks that are all the same size from which to draw. And it's also sort of out of date in favor of simpler memory systems in an effort to reduce energy cost and improve performance. But older machines did use segmented memory. There are a bunch of Intel processors that used it, so we didn't completely make it up. It did exist, it's just more of a historical artifact nowadays. So here is visually a reminder of how a segmented system differs from what we're used to on our machines. Again, there's no cache. All we have is just a single large pool of memory. So already we're throwing locality out the window in the UM's hardware. We also have fewer registers to work with. Most machines nowadays have 32, but we only have 8. And finally, main memory is not divided into contiguous, uniformly sized blocks. Instead, it's more like a pool from which we can create segments. Until a chunk of memory is mapped onto a segment, the program has no way of using it, sort of like memory that hasn't been allocated to your program via malloc. When the is first turned on, when it's initialized, it's given a program to execute, a sequence of machine words, and those words are stored in a special memory segment. The first memory segment that gets mapped during initialization is used to store the program's instructions. So here's the segment that gets mapped. Every segment that we have access to, I'll draw with this gray box. And every segment gets a unique identifier so that we can ask for memory from that segment. Segment 0 is special. That's where the currently running program, where the instructions to execute are always stored. So segment 0 always contains the running program code. Every segment, including the 0 segment, is always broken up into some number of 32-bit words. As the is word addressable, it is not byte addressable. You can't ask for an individual byte of memory. You can only ask for a word at a time, and each word is 32 bits large. So since each instruction is in a 32-bit format, each word of this 0 segment can hold a single instruction. The first instruction is stored in the first word of the segment in big endian mode. So at the lowest address of this segment is where the higher order byte of the word lives. So that's where the opcode lives. So if we were assigning addresses to bytes, which we aren't, it would be byte 0, 1, 2, 3. So here's the first instruction. The second instruction then follows it in memory, again in big endian form, and so on. These instructions can be in either of the two formats we saw earlier in the slides. So these 4 instructions each use the main format, and here we have one load value instruction. Remember, that has the opcode, a register, and a value to load. The determines the next instruction to execute with the use of a program counter. A program counter is simply the address of the next instruction to execute. So you can think of the program counter as it's just a word, it's 32 bits, and its address, it's an address capturing where in this 0 segment the next instruction to execute resides. And that's maintained by the CPU externally from the register file. So you can use in your program some other variable to capture the program counter. You don't have to waste one of your 8 registers to hold it. On each execution cycle, the CPU uses its memory interface to fetch the instruction that's pointed to by its program counter. So it asks for that instruction, which is sent into the CPU. The CPU then decodes it to figure out the opcode, and then extracts any necessary data from the register file, and then finally executes that instruction. And then the program counter is incremented so that it points to the next instruction to execute in segment 0. And that's how the executes a program. It just follows this fetch decode execution cycle using a program counter to keep track of which instruction it's currently on. The program counter is just one way to index into a memory, but most instructions can't use it directly. They need some other mechanism of accessing memory. Each word of memory, each of these individual words, each word that's currently mapped in a segment can be uniquely identified by a pair of integers. Here's the pair of integers. Here's the syntax we use. The first integer specifies which segment we're trying to access. So right now there's only one segment that's been mapped, segment 0. So the only segment we can ask for memory from is in fact segment 0. So this is the segment identifier. Which segment am I trying to get memory from? The second index is an offset from the starting address of that segment. So this says, in whatever segment I've accessed, which is the 0 segment, get me the instruction that's at index 3. So 3 instructions away from the start. So here's the 0th instruction, the first instruction, the second instruction, and the third. It's very similar to like a block offset when we've been talking about cache addressing. The UM's architecture that you will design and implement will guarantee that no two segments have the same identifier. So after looking up the appropriate segment with this first part, the second part of this pair of integers simply indexes into it at the word level of granularity instead of the byte level. Inevitably, you're going to probably want more memory to play with than the 8 registers you already have access to and the 0 segment, which is holding your program's instructions. But currently, the only accessible memory is segment 0. We haven't mapped anything else. So to get a fresh segment of memory, we use an instruction to map it from the existing pool. For example, you can use the map instruction to give you a new segment with a new unique ID, and you can tell it how many words it should be able to hold. So if I say, hey, map me a new segment and make it big enough to hold 5 words, the will allocate that memory for you, create a new segment, make sure it can hold exactly 5 words, and generate a unique identifier for it. You can then do a segmented store instruction, which just means take the contents of a register and store it in a mapped segment of memory. You can also do segmented loads, which look like this, where you grab a word from a specific segment and load it into a register. Ask yourself, based on this instruction, which segment am I trying to access, and which word of that segment am I specifically accessing? And then which register will that word be stored in? The answer based on this is I'm accessing memory in segment 1. The first integer is the segment identifier, and I'm accessing the word at index 1. So counting from 0, I am accessing the 0 first word in segment 1 and storing that in register 3, 0, 1, 2, 3. When the program is done using a segment, it should unmap it so that the resources can be given to other parts of the program that might need it. The unmap instruction just takes in a segment identifier, makes sure that there is a segment with that ID, and then returns it back to the pool so we can no longer access it. This is really similar to the notion of freeing allocated memory, except you should try to use your unused segment IDs to provide as much memory to the program as possible. So now that we're no longer using segment ID 1, if I ask to map a new segment, we should be able to reuse that identifier again so that you don't run out of identifiers by accident. So here's a summary of the segmented memory system. Segment 0 is special. That's where the running UM's code is always located. The emulator, when it first starts up, arranges for the initial code that's passed in a file to be stored in segment 0. Other segments can be copied in to segment 0 and replace its current contents. This is what the load program instruction does, and it lets us change what code is running on the fly. The program, through its instructions, can map, use, and unmap other segments to hold data as necessary. It's the emulator's job, your C program's job, to keep track of which segment IDs map to the actual data, which segment IDs are available for new segments, and keeping track of these two things is going to be a significant part of your work on homework 6. Remember, it's up to you of whether or not you would like to use standard C arrays for these segments, or you can use Hansen-style data structures. It's up to you. But there are some performance requirements that you need to strive to achieve that using certain abstractions could prevent you from doing so. So make sure you read the spec about what we're expecting from you in terms of performance. All right, here's a summary of what we've gone over today. You should review the entire The way that it works, it has 14 simple instructions. And what you're going to be doing for homework 6 is creating an emulator, which in itself is an important and powerful concept. Emulators can be used to test code for a new machine before the machine exists. They're used to prove that a machine design works. And you can also use them to evaluate the performance of machines and just learn more about them in general. To build the simulator, you're going to need to consider the state that you need to keep track of at each time step of emulation, the logic that executes your instructions, and any interfaces to say the memory system, the IO system, things like that. You'll find that your emulator will be using many abstractions that somehow match the real hardware being represented. And you're going to have to grapple with the notion of a segmented memory system. We're using it here because it will let us address more memory than just what 32 bits would normally let us address. The segment IDs are used to select what appear to be these smaller memory segments that are each addressed from 0. And it's basically your emulator's job to somehow map segments to the flat underlying memory of your actual machine architecture. So I hope that you found this lecture illuminating. Again, please come with questions. I look forward to seeing many of your bright, shining faces in class and in my office hours. Miss you.